If f is an extended real valued function whose domain is measurable, then the following are equivalent for each real number alpha. So all these statements are equivalent to each other. This we need to show. So first we are going to imply that A implies D and D implies A, right? That A is equivalent to D. Let's show this first. Solution. Let's take domain of f to be D, right? And we are going to show that A is equivalent to D. For that, I need to show that A implies D and D is implying back to A, right? What is D part? All those x such that, what is D part? All those x such that fx is less than equal to alpha. So all those x such that f of x is less than equal to alpha, and we need to reach that all those x for which fx is strictly greater than alpha. How can I write this further? If I subtract all those x for which f of x is greater than alpha from the domain D, then I am getting this set. Now this is equal to what? This is the measurable set. Domain itself is measurable. So this set is equal to the difference of two measurable set. And the difference of two measurable set is itself measurable. So we have used this A part to prove that this set is measurable. So hence all those x for which f of x is less than equal to alpha is measurable. So which means the part D is measurable, right? And now we are going back to from this part D to the part A to show the part A to be measurable set. The A part is all those x for which f of x is strictly greater than alpha. This is your A part. I need to show that this is measurable. And what is given to us that this D part is measurable. We are going to use this. And this is nothing but your D part, which is measurable set, right? So domain is also measurable. This is set is also measurable, which means the difference of two sets is measurable set. So hence x for which f of x is strictly greater than alpha is measurable. That means A part is measurable. We have shown now. So we have shown that A is equivalent to D. Let's prove now A is equivalent to B. We have already shown that A is equivalent to D, and now we are going to show that A is equivalent to B, which means we have to show that A implies B and B implies A, right? Okay, now using A, I'm going to prove first the B part. All those x for which f of x is greater than equal to alpha. I have to show that this is measurable. How to write this set to be equal to? I have to use the part A over here. What is part A? All those x for which f of x is strictly greater than alpha. This is measurable set given to us. I need to use this A part in this B part to show that B is measurable. So how should I write this set to be equal to? Yes? No, we cannot subtract the set from the domain. If you are thinking like before in the previous part, that if I subtract fx strictly less than alpha from this, no, then this will not work because this is not given to us to be a measurable set. What is given to us that fx strictly greater than alpha is measurable. So I have to use this greater than sign. I have to keep in mind this greater than equal to sign. So I have to use this condition. So we cannot subtract the set from the domain to show easily that B is also measurable. No. How to write this to be as? Yes. So these are all equal to the intersections of a sequence of measurable sets. And the intersections of the measurable sets is measurable. The sequence of measurable sets is measurable. So hence, all those x for which f of x is greater than equal to alpha is measurable. So we have shown that A implies B, right? And now we have to show that B implies A. What is A? It is all those x for which f of x is strictly greater than alpha. This is A part. I have to show that this is measurable, and I have to use the B part to show this. What is B part? All those x for which fx is greater than equal to alpha. How to write this now? Subtracting from the domain does not work because here we are having the greater than equal to sign, right? Okay. Writing here this to be as the unions of all those x for which f of x is greater than equal to alpha plus 1 by n. And n is going from 1 to infinity. So this is equal to the union of measurable sets, and the union of measurable sets is measurable. So we have shown that this A part, all those x for which fx is strictly greater than alpha, is measurable. So we have shown that A and B are equivalent. Remaining to show that now B is equivalent to C. For that, we have to show that B implies C and C implies B, right? So now B implies C. What is C part? All those x for which f of x is less than alpha, right? And what is B part? All those x for which f of x is greater than equal to alpha. Now I am having the opposite signs over here. I can now subtract the set from the domain. Yes. So subtracting what set? All those x for which f of x is, because here it is less than alpha. So I have to subtract all those x for which fx is greater than equal to alpha. Right, this B part. And this is your B part which is measurable. D is also measurable. So it is equal to the difference of the measurable set. Difference of the measurable sets is measurable set. So that is, we have shown that C part is measurable. Now to show, so we have shown that B implies C. And now we have to show that C implies B, the reverse. What is B part? It is all those x for which f of x is greater than equal to alpha. To show that this is measurable, how can I write this as? Because I need to use the C part, that is all those x for which f of x is strictly less than alpha. To use this part, I have to subtract from the domain this set itself, because here it is fx greater than equal to alpha. So subtracting the set, all those x for which f of x is strictly less than alpha. So this works. And because it is measurable, and it is again the difference of the measurable set, which is measurable set. So again it is the difference of the measurable set, and the difference of measurable sets is measurable. So using the C part, we have shown that B part is measurable, right? So B part is a measurable set. So we have shown that B is equivalent to C. So all the following statements, hence all the statements are equivalent now. There is no need to show that C implies D, because it is obviously, because what is C? C is equivalent to B, B is equivalent to A, and A is equivalent to D, which implies C is equivalent to D on its own, right? So hence we have shown that all these statements are equivalent. All right, thank you.